Hello, this is reading material 2 for the course Physics of Soft Condensed Matter. My name is Nishant Sachdeva. My roll number is 2018 111040. In this paper, we studied two algorithms which are used to compute projected correlation functions in molecular dynamics situations. So basically what happens in this paper is there's an explicit derivation of the Mori-Zwanvik orthogonal dynamics of observables. Exactly what this is we'll study ahead. This leads to two practical algorithms which are used to compute exactly projected observables, not random etc. but like exact. The random noise is modeled perfectly. And projected correlation functions, example the memory kernels. Now the algorithms that we develop here, these two algorithms, they are then applied to study the diffusive dynamics of a tagged particle in a Lennard-Jones fluid. Again, too many terms here, we will study them as they go ahead. So Lennard-Jones fluid, tagged particles, diffusive dynamics. Keep in mind these words. Now, the properties of the associated random noise and the decomposition of the corresponding memory kernel will also come as we go ahead. So now how we'll study this is in a different way. We will not go leniently to the paper. What we'll do is we'll go through the introduction, then we'll go over to the conclusion section, study that. So how that will help us is that we will get a sense of what the problem is by the introduction, and we will get a sense of how the solution has been modeled and how it works by the conclusion. So when we go to study the mathematics after that, which by the way is pretty complicated actually. Once we have the idea of what the problem statement is and how the conclusion works, we will get a much easier way to study the mathematics of it. So here we start. So now the introduction. So what they're talking about is that so every subsystem has an environment around it that influences it. So every subsystem, it has its functioning, its dynamics, etc. The environment around it influences it, and that influence has two components: a random force that can be exerted by the environment on a small system, and a friction force. The friction force is basically sort of a feedback thing that describes the response of the environment to the dynamics of the subsystem. So one is directly influencing the subsystem through a random force, and the other is a frictional force. So the response of the environment is like it's not instantaneous. It's basically a somewhat retarded. So how it happens is there's something happening in the subsystem, and the response comes after the slight delay. Also, the environment is keeping a memory of the past dynamics. So whatever has happened so far will have an effect. It's not completely independent of the system's history, let's say. So the contraction of information that occurs when only the dynamics of the subsystem is considered. This time I think what they're saying is that the history of the system is not considered, only the current dynamics of the system are considered. This particular contraction of information, so basically we're losing out information here. This was formalized by Mori and Zwanvik. These guys introduced the formalism of projection operators to single out the relevant degrees of freedom. Formalism of projection operators, this is what they used, and they used this to single out the relevant degrees of freedom. So what happens is that the approach that they're providing, it does not only generalize Langevin equation, which governs the evolution, but it's also an explicit expression for the memory kernel, that describes the retarded force. Let's go through this part again. So what they are doing is they introduced the formalism of projection operators, which helped in singling out the relevant degrees of freedom. So this approach did not only generalize Langevin equations for us and governed their evolution, but it also gave an explicit expression for the memory kernel that described the retarded force. The fluctuation theorem that comes after that, it stipulates that it is equal to the correlation function of the random force. So now, So the recent experimental developments in particle tracking. So basically what happens is we have a box and there are particles. And normally what happens is they randomly move around. They're not easy to track, but there have been recent developments, technological developments that help in tracking, and they have allowed for the measurement of the random force or colloidal particles. So the colloidal systems we have here, particles have a random force coming on them, and now we're able to track what that force is. And thereby how it helps us is that it provides experimental tests of our theoretical model. So we can theorize whatever we want, but ultimately we need to test it. So that's what happens. So recent technological developments have helped in that area. And again, so once we are able to test our models, we are able to see if the memory thing actually works or not. We say it has memory, but what exactly is meant by memory, that and all we are able to study. Now, the determination of memory kernels and the extraction of the random force from molecular simulations have remained elusive. So this is something that we have to live with. Basically, we have good technology, we can see what the random forces are, but we cannot completely figure out how things work. So what we don't have yet is the determination of memory kernels and extraction of the random force from molecular simulations. This is something we don't have yet. The difficulties of why we don't have them is because of the fact that the orthogonal dynamics that enter the definition of the memory kernels cannot be described as a flow in phase space, and one needs to propagate observables instead of configurations. So what's happening here is that the orthogonal dynamics that enter the system, or it's the definition of memory kernels, that cannot be described as a flow in phase space. And because of that, one needs to propagate observables instead of configurations. So the usual method to extract these memory kernels is, so once we've seen what the issues are, the usual method we get is through inversion of the generalized Langevin equations. Be careful of that, this name is going to come up ahead quite a lot, the GLE. So the usual method is through the inversion of the generalized Langevin equations. These use Laplace transforms or through rewriting of GLE as a Volterra equation. So what they're saying is that, okay, we have an issue here, and to solve that what we'll do is to solve that. So what was the issue? The extraction of memory kernel, and that wasn't happening with normal technology. So for that we use the inversion of the generalized Langevin equations. How we do that? We use Laplace transforms or through a rewriting of the GLE as a Volterra equation. New name here, Volterra equation, keep note, Volterra equation. Now we have this method, sure, but these methods do not yet allow for a decomposition of the memory kernel into different contributions. So we have memory, but now what all makes up it, or what all makes it up, we don't yet have a way to figure that or break that down. So these methods can help in extraction of the memory kernels, but they cannot yet help us decompose it into different contributions. Now there's yet another approach which consists in fixing the subsystem by assigning to it an infinite mass. So what happens is we make the subsystem so-called so big that it's not really a subsystem anymore. So the environment effects go down. So the memory kernel basically then becomes a standard correlation function, and a decomposition is performed easily. Makes sense. However, this approach modifies the dynamics of the system. Also makes sense. We have assigned it infinite mass, so something's going to change. Now we describe further. So in the paper, what happens is there are two algorithms to extract memory kernels from molecular dynamics simulations by explicitly propagating observables according to the orthogonal dynamics. Check here. So what they were saying is that what they said that, okay, one needs to propagate observables instead of configurations. And that's exactly what they're doing. They're gonna propagate observables according to the orthogonal dynamics. We illustrate these algorithms on a simple case. So we is the people who wrote this paper. They have illustrated these algorithms on a simple case, which is the Brownian motion of a tagged particle immersed in a Lennard-Jones fluid. Three terms here. Brownian motion, we know what that is. We studied that in the previous paper, in the reading material 1, of a tagged particle immersed in a Lennard-Jones fluid. So by performing explicitly the projection operation introduced by Maury and Zwanwig, we saw them here. So these guys had worked out a projection operation. That's what we'll use. We are able to extract the random force, which then allows for a direct test of its properties at atomic scales. Now the paper itself that we go ahead is organized as follows. So in section 2, this is section 1 right now, they'll describe the theory of this projection, these projection operators, and they'll introduce the two algorithms to compute orthogonal dynamics of observables. After that, they'll discuss some statistical properties of the Morris one-week random force. We got the and we use the theory. We use the theory. Then we got the two algorithms to compute orthogonal dynamics, and then they'll discuss the statistical properties of the Morris one-week random force. In the next section after that, they'll present numerical results for the diffusion of a tagged particle in the Energy-Jones fluid. This we studied before. So the particles, they have been tagged and they'll be studied there. Then they'll study the corresponding friction kernel. Some friction was the force that was coming out. Right? So this friction and this random force. So they'll study the corresponding friction kernel, some properties of the random force, and finally they'll help show how the decomposition of the friction kernel in short range contributions happen. So now what we'll do is we will go to the end of the paper and study the conclusions of the paper. How that helps us is that we get an idea of what the methods are being used. Once we have that, it will become easier for us to study the mathematics of it. So as we see, they have given the simulation results here, by the way. So what happens is there's theoretic here, then they've shown how the results work. And after that, what they have gone to the conclusions. So now the conclusion. So what they have done is they have developed, again, like we know this part. So they have developed the two algorithms for the computation of projected correlation functions for any pair of observables. So what this pair of observables are, we'll get to know. So these algorithms basically they are based on a suitable propagation of observables. I'm gonna be using a lot of black boxes here because we haven't studied the whole paper yet, but we're gonna assume black boxes so that we can form an over-the-top idea of how things work. So these algorithms are based on a suitable propagation of observables measured at a given phase space points. Let's go again. They are based on suitable propagation of observables which have been measured at given phase space points. So one algorithm which denoted forward orthogonal dynamics, looking back, is based on the forward orthogonal dynamics. It needs the whole trajectory to be known in advance. The first algorithm needs the whole trajectory to be known in advance, and hence it is implemented outside the MD simulation itself. Fair enough. The second algorithm, backward orthogonal dynamics, where we look ahead, that uses a propagation of the observables backward according to the adjoint of the orthogonal dynamics. Although this adjoint dynamics is less natural, but it can be implemented alongside the MD simulation. So what we have understood here is that there are two algorithms. One is forward orthogonal dynamics, which looks back. It is based on the forward orthogonal dynamics. It needs the whole trajectory to be known in advance, and is because of this purpose implemented outside the MD simulation. The second algo, backward orthogonal dynamics, looking ahead, that uses a propagation of the observables backwards according to the adjoint of the orthogonal dynamics. This is a bit less natural, it's a bit less intuitive, but it can be implemented alongside the simulation. So it does not need to be implemented outside the simulation. The first algorithm needs to go outside the simulation, the second can be implemented along the simulation. That helps. So as a test application, the motion of a tagged particle in the LJ fluid, Lennard-Jones fluid, the two algorithms were shown to give identical results and to be quite stable. Both the algorithms gave identical results, which means they're compatible, which means they're working correctly, and they were quite stable. So less chances of errors, they're not very prone to errors, there are not many corner cases there, so they work. The algorithm forward orthogonal dynamics also allowed us to extract the random force, or which we call noise, in order to study its properties. So this guy forward one helps us to get the noise part, and then we can study it. The computed random force then showed a clear non-Gaussian statistics. That's also important. Usually Gaussian comes out a lot, but in this case the noise information that we got, the computed random force that we got, it showed clearly non-Gaussian behavior. Finally, since the algorithms can be used to propagate any observable according to the orthogonal dynamics, since it can do that, it was possible for us to separate the long range and short range contributions of the Langevin kernel. This is an important part. So since the algorithms can be used to propagate any observable, that helped us separate the long range and short range contributions of the Langevin kernel. Then we showed that the short range or short term is the major contribution to the overall friction. Keep these in mind because this is something we haven't studied yet. We know what's happening, so keep in mind the black boxes that are coming along. So we know that okay, there's something called a short range and a long range forces, and the major contribution to the overall thing is the short range. Although again it's major, it's not complete, so other terms are not completely negligible. The short range correlation function is also the most affected by going from normal correlation function to the projected correlation function. So it has the most effect and it is also the most affected when we change the correlation functions. Now, the proposed algorithms, thus, they pave the way for the analysis of the origin of the friction kernel and the total friction exerted on the relevant degrees of freedom. So two things, the friction kernel and the entire friction force that is exerted on the relevant degrees of freedom. For instance, it may be used to study the effect of confinement and the different roles of the solvent and the confining material. So two things here, confinement ka effect and the different roles of the solvent and the confining material. We have recently applied it to the case of ions confined in clay materials. This is another paper. This is not this paper. Keep that in mind. It also allows to straightforwardly study projected correlation functions that are not simply force correlation functions for describing the non-instantaneous response to the dynamics of the relevant degrees of freedom. Yeah, I'll read this part again. It's a bit tricky. It also allows us to straightforwardly study projected correlation functions that are not simply force correlation functions, which if it were could have been used to describe the non-instantaneous response to the dynamics of the relevant degrees of freedom, as for the non-local response of the surrounding to the motion of a Brownian particle. We are currently investigating, so we are currently means this is what the people who wrote this paper are working on. So they are currently just investigating the long time behavior of the memory kernel in order to assess the relevance of the usual approximations. Overall, these algorithms provide a new tool to bridge the gap between fully atomistic models and effective dynamics described by the generalized Langevin equations. We have a fair idea of what they do here. We have little bit of the structure of the algorithm over there. So now that we know that, we can actually go and start studying the mathematics of it. It's a bit involved. We're going to have a lot of black boxes and we're going to have to study outside the scope of this paper to actually fully grasp what the paper is doing. So we start with the theory now. First part, the Maurice-Van Wyck projection. Now, this theory, the Maurice-Van Wyck theory, it's a framework that describes the evolution of any observable given the evolution of a set of relevant or macroscopic variables. So we need a set of relevant or macroscopic variables, and once we are given that, we can describe the evolution of any observable. Typical examples of this thing include the properties of a tagged particle. Now, the tagged particle's properties have been given in these papers. We're not going into them right now. But the former thing basically, so what happens is the Maurice-Van Wyck theory, it's a framework that describes the evolution of any observable given the evolution of a set of relevant macroscopic variables. Though what happens is they generally refer to the collective variables such as the coarse grained density, momentum, and stress fields to derive hydrodynamic equations. Again, reference to other papers. Now the discussion that we do here is very general. It's like pretty over the top, but we will also consider as a practical application the case of a diffusion of a tagged particle in a fluid and use its momentum as the relevant variable. So that's what we study basically here. We have the generic description of how this works, and then we study the proper example, which is the diffusion of a tagged particle in a fluid and using its momentum as the relevant variable. Therefore, we will use the notation P for generic relevant set of variables. Normally P is used for momentum, but for our purposes here, it's capital B, by the way, not small p. So P here will denote a generic relevant set of variables. Any observable B is this phase space function B, which is a function of Q and P of the atomic positions Q. So this is Q and P. P is a generic relevant set of variables and Q are the atomic positions. And momenta is the actual P. So just note the difference here, okay? This capital P is a relevant set of variables. Small p is the momentum. Q are the atomic positions. Here we consider a Hamiltonian system, I mean, this is pretty generic Hamiltonian. There's nothing special in this. Now, with the Hamiltonian, and where Qt and Pt that we see here, they refer to the positions and momenta after a time t. They start from the initial phase state point Q comma P. Now the value of the observable B are the observable and observable B we see here. So B is an observable. The value of this observable B at any later time, or what we call as T, is denoted by Bt, which is a function of Q and P, as B of Qt comma Pt. So B at time t will depend on the Q at time t and P at time t. It evolves according to the Liouville equation, that is d of bt by dt is ILBT, where IL is the Liouvillean super operator with the Poisson bracket. Now be careful, we did the Poisson brackets in the previous paper. Observe here, okay? The value of the observable B at this later time is denoted by B of Qt comma Pt. So the value of B at time t depends on the Q and P at that time t. This evolves according to the Liouville equation dBt by dt, which is ILB. This could be a Greek symbol, but we're calling it L for our purposes here because I don't know what the symbol is otherwise called. So where IL is the H and dot with the Poisson bracket. This equation basically may be formally integrated to give the evolution of B. That is, Bt is e to the power ILT B naught. B naught is the initial value. Keep this part in mind. So this will come ahead as we go ahead. This will come up later. This will come up later. Now, the purpose of the Maurice-Van Wyck formalism is to express the evolution of B only in terms of that relevant variable P instead of the full phase space Q comma P. So for that purpose, for that aim, a projector operator P is defined in the space of observables. A projector operator. So what we see is that the purpose of the Maurice-Van Wyck formalism that we're studying right now is to express the evolution of B. Basically, right now it's a function of E and B naught and I and L and T, but we want it to be expressed as a function of only in terms of the relevant variable P instead of the full phase space. So we don't want Q to be involved, we don't want everything to be involved, we only want the final P. For that purpose, a projector operator P is defined in the space of the observable. So this is the projector operator P. We apply this on B and we get this particular equation for that purpose. Depends on P naught. These two are both average magnitudes. No, again, so that's what they're saying. This symbol means an average over the stationary distribution corresponding to the evolution equation. Equation 1. So equation 1 is this guy. They're saying is that this particular symbol means an average over the stationary distribution corresponding to the evolution equation 1. Now, together with the operator Q, that is 1 minus P. So P is already an operator that we defined by this. So the Q is a new operator now, which is 1 minus P. The observable B can be decomposed into a contribution along the relevant variable P and another one orthogonal to it. Q is the second operator that we are describing here, and by using these two, we can make sure that the observable B can be decomposed into a contribution along the relevant variable, one contribution along the relevant variable, sorry for this. One contribution along the relevant variable and the other one orthogonal to it. So the Maurice-Van Wyck that we studied later, theory is then based on Dyson's operator relation. I'm assuming it's this guy here. It's a bit complicated to look at, but that's what it is. So that's e to the power iota lt minus u, pi l to e to the power iq lu q du plus e to the power I q lt to q. Now we know that e to the power iota lt is e to the power iota lt p plus e to the power iota lt q. So that's it. That is its contribution along two variables, because one is q plus p. So we have one contribution along p and the other along q. So it is then possible to express the evolution of the observable b as, so this was the actual variable. Now we have e to the power iota lt as along p and q, so that we can substitute up here. B as e to the power iota lt b is e to the power iota lt b p plus e to the power iota lt b q plus this particular integral. Now applying this relation to the rate of change of an observable a, applying this relation to the rate of change of an observable a, we get observable a's rate of change is this particular thing here. Once we apply this relation to this observable a's rate of change, we obtain the GLE. What was GLE? Remember here, GLE was a generalized Langevin equation. So we obtain the GLE. So we get the GLE. Okay, so that is a to the at dot is dat by dt. That is I omega a pt minus the integral ka of u p of t minus u du plus rt. With I omega a, let's call the symbol omega for now, is this system of averages, and ka of u, so notice these are the new terms that are coming here right now. Of u is the average of p naught dot I e to the power I q lu q e naught dot, that's average, and then the average of p naught square. Now equation 5 here, this particular equation, it describes the dynamics of at dot as the sum of a systematic and a random distribution. A systematic and a random contribution. So the systematic contribution is itself composed of a reversible term, which is equation 6. So this is the systematic contribution, and the retarded one involving the kernel, that is in equation 7. So this kernel here, both depend only on the evolution of a relevant variable p. Relevant variable p. The third term, equation 8, the third term rt, this guy, sorry, this is the third term here. The third term RT accounts for the effect of the other degrees of freedom which have been projected out. So the relevant ones are here. The ones that got left out have been taken care of by equation 8. This contraction of information, I'll just change the color for the purposes of ease here, because it's the same color coming from many often names. So this contraction of information, so we're losing some information because of losing out the degrees of freedom which got projected out. So this contraction of information renders the evolution of this term more difficult to apprehend, thus appears as fluctuating or random. Which makes sense. Now, as mentioned above, we saw that above here, an efficient approach to the diffusion of a tagged particle in a fluid is to consider its momentum as both the relevant variable p and the observable a. We have issues right now, so what we could do, what a better method would be to consider the diffusion of a tagged particle in a fluid, to consider its momentum as both the relevant variable p and the observable a. In that case, when we do that, the time derivative of both quantities is the force acting on the particle, and the denominator in the equation 6 and 7 is equal to mkbt. M is with m, kb and t the usual as they are. We'll read this part again because it's a bit complicated again, so I'll just remove these things. It's a bit complicated, so we'll read this part again. There's no issues with that. So, as they mentioned above, an efficient approach to the diffusion of a tagged particle in a fluid is to consider its momentum as both the relevant variable p and the observable a. When we do that, the time derivative of both quantities is the force acting on the particle. And the denominator in equation 6 and 7. So 6 and 7 is denominator here, and denominator here. So p naught square is average, is equal to mkbt. With m we know the mass of the particle, kb is the Boltzmann constant, and T is the temperature. In addition to that, the reversible term equation 6 vanishes, and the term defined by equation 8 is a random force. Note here, The reversible term in equation 6 vanishes. The term defined by equation 8 is now only a random force. By this analogy, we will refer in the following coming up ahead. F as ILP as a force. We refer to ILP as a force and to P square as a kinetic energy. Even in the case of a generic variable, because we know that okay, once things work out, it becomes that only. So we note that in this case, in our case, the memory kernel reduces to the autocorrelation function of the random force. How that happens, we will see ahead. So far, we know that okay, this thing happens. How exactly, we will see ahead. So one then usually assumes the particular properties for this random term. So once we assume that okay, so and so once we assume that okay, ILP is a force and P square is a kinetic energy term, we assume that the random term and the once we get these two terms, we assume their particular properties, even if it's only for a generic purpose. So the most simple and widespread Markovian assumption, Markovian models are very popular in probability classes. So that's what we are assuming here, which becomes exact in the limit where the ratio between the mass and of the considered solute and that of the bath molecules tends to be infinity. Read this part again. It's a bit tricky. It's getting a bit tricky now. So like we said, the mathematics is involved. So after we did all this, we assume particular properties for the random term and the corresponding memory kernel. The most simple and the most famous actually Markovian assumption, which becomes exact in the limit. Now it's an assumption so far, but it becomes exact when the ratio between the mass of the solute and that of the bath molecules tends to infinity. So when the bath molecule and the solute are very different in sizes, that's how the ratio goes to infinity. So the Markovian assumption considers a Gaussian distribution and a vanishing correlation time for the random force. The Markovian assumption considers a Gaussian distribution and a vanishing correlation time for the random force. This results in a memory kernel Ku, which is gamma delta of u, with delta as the Dirac distribution and the friction gamma as the integral over 0 to infinity Ku du. So long time correlations due to the solvent backflow around the solute can be captured within the framework of continuous hydrodynamic theories, resulting in Ku being proportional to minus u to the power minus 3 by 2. This captures the resonances observed experimentally in polar particles. What they're saying is that okay, for a short time we can go ahead with this directly, but for a long time where reverberations can happen, we need to make certain assumptions, which we do here. So now we'll be studying in detail the projected correlation functions. So the memory kernel Ka of t, which we use to determine the retarded contribution, that involves the correlation function of the random term r and the derivative of the relevant variable p dot. Now it differs from the standard time correlation functions in that the dynamics entering the correlation function is not the normal dynamics. That's where it differs. It's not the normal dynamics, but the one modified by the Mori projector and the generalized IQL. What they're saying is that the memory kernel Ka of t, which determines the retarded contribution, it involves the correlation function of the random term r and the derivative of the relevant variable p. How it differs from the standard time correlation functions is that in the standard ones, the dynamics entering the correlation functions are the normal ones, which are generated by the Liouvillean IL. But in our case, the ones we are using are the ones modified by the Mori projector and generated by IQL. Such projected correlation functions can be defined for any pair of observables A and B as this particular equation. So CAB tilde of t is defined as the average of A naught e to the power IQLT B naught. Now this, although we defined it, we cannot compute it directly from the values of these observables along the trajectory. This has to be taken in care of. We also note here that in particular that this particular definition depends not only on two observables but also on the choice of relevant variable p via the projector q. So projector q was 1 minus p. So the by choice of p comes into picture here. Since the operators LP and Q are Hermitian for the scalar product, it's a revelation here, but they are Hermitian for the scalar product. We know this part. So since they are Hermitian for the scalar product, the projected correlation functions can also be rewritten as, so just check here. So what they're doing is they can actually do this part. So they can change the orders around because actually the thing is all Hermitian. So the sign changes and the order can change. Note here the inversion between Q and L in the propagator. This comes into picture here. So now that we've done all this, we will discuss two approaches to extract projected correlation functions by adopting complementary points of view corresponding to equation 9 and 10. Point 1 and point 2. These are two different things. Just take note of that here. They are two different things here. They both come to the same part. That's good for us, but they're actually two different things. Complementary points of view, let's say. So now what they're saying is that they'll discuss two approaches to extract these correlation functions by adopting two different points of view, which is equation 9 and 10 respectively. So to that end, for the purposes, they will introduce this operator called Vt plus. This is defined as e to the power iqlt b naught. This propagates the observable b forward in time. Fair enough. So during a time t, according to the orthogonal dynamics generated by IQL. So what it does is it propagates the observable b naught forward in time according to the orthogonal dynamics which are being generated by this particular guy, IQL. This observable thus coincides with b at t equals to 0 and evolves according to this guy. So we wrote this equation. We said that okay, this propagates the observable b in time according to this particular dynamics which have been given by this IQL. So this observable that we made just now, it coincides with b at t equals to 0 and it evolves according to this particular equation. Similarly, we define A. So similarly, we discussed. So we define B as e to the power iqlt. Now we define A as at as e to the power minus lqt a naught. This guy propagates the observable A backward in time. This guy goes forward in time. This guy goes backward in time. Now during a time t, according to the orthogonal dynamics, it coincides with A at t equals to 0 and evolves according to this guy. So note the sign changes, note the notation changes. This guy A is going backward in time, the B was going forward in time. So the projected correlation function CAB of T can then be written as two different seemingly usual correlation functions. We're just simplifying things now, but which is actually good. So in the following portion that we go ahead now, we will introduce the two algorithms to compute CAB of T using these two expressions, 1 and 2. These are basically our two algorithms. We will then discuss the properties of the random noise before we turn to the results from molecular dynamic simulations. Now we will go to the forward orthogonal dynamics looking back. So what we said was we'll study the two algorithms. First, it's the forward one and then it's the backward one. We'll go to the backward one later. First, we'll do the forward one. So while equation 13 provides convenient expressions of CAB of T as a normal correlation function, the observables BT plus and AT minus evolve according to modified dynamics, and thus they cannot simply be measured at each time of the trajectory. So we first describe an algorithm to compute the observable BT plus, which evolves according to the forward orthogonal dynamics. Let's repeat that then. Apologies for the noise there, so we'll repeat this part now. What we are doing is, so equation 13 is this guy right here. It provides convenient expressions of CAB of T as a normal correlation function. The observables BT plus and AT minus, however, they evolve according to modified dynamics. We change things around here, right? Modified dynamics, and thus they cannot simply be measured at each time of the trajectory, which is okay. So we first describe an algorithm to compute the observable BT plus, which evolves according to the forward orthogonal dynamics. And thus the projected correlation functions by equation 13 as shown in appendix A. In appendices, we're not going to go to them, they're still part of the paper, the mathematics is there. but we leave it to the reader. We are not going to go into the detail of that mathematics. So the projected correlation functions by equation 13 as shown in appendix A, BT plus satisfies this particular relation. So BT plus of Q and P is BT of Q and P, which is the previous time slot, plus the integral of 0 to T, P of T minus U, Q of P. So P of T minus U as a function of Q and P into the average of F naught BU plus divided by the average of P naught square. We can then write this expression at time T plus delta T and separate the integral between 0 and T on the one hand and between T and T plus delta T on the other. So 0 to T and then T plus delta T. Noting that for an observable D evolving under the normal dynamics such as P or B, we have by definition D of T plus delta T Q comma P is dt Q of delta T P of delta T, which is the normal one. This would have been there if the dynamics were normal. And finally, we make the change of variable U to U minus T in the remaining integral. Once we do all that, so once we change U to U minus T, we obtain B of T, B plus of T plus delta T, Q of P is BT plus Q of delta T, P of delta T plus 0 to delta T of P of minus U. So T minus U becomes minus U when we put U as U minus T. So P of minus U, Q of delta T, P of delta T into average of F naught P of B plus of T plus U divided by average of P naught square. In principle, basically what we're saying is that several numerical schemes can be used to discretize the integral. This integral needs to be discretized, needs to be converted to a possibly summation, which makes life easy for us. The most simple form of doing that, of converting the integral and discretizing it, goes as, so we do this thing here then. So the BT plus part remains the same. The integral is split like this. This basically is easily implemented from a molecular dynamics trajectory of length and drag steps as follows. So once we discretized it and converted the integral to a summation, we will take arrays now to sum it. So this whole process can easily be implemented from a molecular dynamics trajectory of length and drag steps as follows. The observables A, P and F, A, P and F and BT plus are stored in 4 arrays. So these are the 4 arrays that are being stored, with M obviously belonging to 0 to the number of molecules and number of frames in the trajectory. Now delta T is the time step of the molecular dynamics. So not every time step is 1 second. Sometimes the time step have to be shorter so that we can actually capture what's happening. The first three contain the value of APF for each configuration along the whole trajectory and are never updated during the procedure. The last one, this guy here, evolves iteratively for n belonging to each and every configuration. So one by one it evolves. Where n core is the length for which one wants to calculate the correlation. Starting from the initial values B0 plus of m, we then when we're iterating, we get this particular equation. So the starting one is this guy as our initial value. For iterating, we get this with beta of n, this guy beta of n being here. Just do this thing here. Doing all this allows us to reconstruct the evolution of BT plus from each configuration along the trajectory. So now we're not taking a full whole picture view, we are doing it for each trajectory, each configuration along the trajectory. And it allows us to analyze its properties. So now obviously since we can check it frame by frame, we can also analyze it frame by frame. That gives us a better amount of data and better amount of understanding of how things are working. In particular, the kernel CAB is calculated for T equals n delta T from equation 13. Equation 13 is this guy. And the scalar product of the arrays A0 and Bn plus is this guy. The arrays. So summation of A0 of m and B0 plus. So that's the scalar product. Now, as mentioned above, in the case where P is the momentum of a tagged particle, F is the force acting on it, and P square is proportional to the thermal energy. This average basically that we have can then be computed with a better accuracy using the instantaneous kinetic energy in the interval m belongs to 0 to n traj minus n minus 1. Now, let's redo that part. So, what we're saying is that the average can then be computed with a better accuracy using the instantaneous kinetic energy in this interval instead of the average temperature over the whole trajectory. So, we're doing, instead of taking over the whole trajectory, we're taking it frame by frame. We named this algorithm according to the fact that we correlate the observable BT plus evolved forward in time according to the orthogonal dynamics IQL from the initial condition with the observable A at the initial time, that is looking back. So A looking back and then B keeps going forward. This algorithm requires O of n traj of memory size and the calculation time is O of n traj into n cos, so approximately n square, but it can go anywhere and above depending on that. This finishes our forward orthogonal dynamics algorithm. We had to do two algos, the first one is done. Now we'll work on the backward orthogonal dynamics where we look ahead. So in this approach, we introduce an auxiliary operation 8t tilde minus as a to the power ILT 880 minus, which let's call it 80 dash or minus, it's the same thing. Doesn't really make a difference. Mathematics is the same. This coincides with a at t equals to 0 and evolves as, so you will not see the appendix B, the mathematics is there in detail, you can see it. But it evolves as this particular integral. So that's dA tilde t dash for dt is minus IL pt a tilde t dash. Here we have defined a time dependent projection operator pt. They're calling it p tau here, but it's also pt. So let's just call it pt. Or let's call it p tau, it's fine. So p tau is e to the power IL tau p IL minus IL tau. Kind of sounds like the SVD we do there because it's like ILT and this minus LT. So this projection, this operator is the projection on the relevant variable p at time tau. The projected correlation function, therefore, what we get is CAB of t is average of a t tilde dash q of p b naught qtpt average. That is the correlation function between a tilde t dash and b at a time t forward in time. The value of a tilde t dash at phase space point q comma p is however updated according to dA tilde t dash q comma p upon dt is pt at dash by p naught square's average ft of q comma p. The structure of these equations allow for the computation of the correlation function on the fly, contrary to the previous method which requires generating the trajectories as a prior step. So here we were dealing with the fact that the entire trajectory is there with us, then we process on it. But here we can compute things on the fly, right there on the spot. We first choose the number of consecutive steps n average to compute the averages. At each time step t equals to n delta t around the dynamics, we consider again 4 arrays, analogous to what we did above. For n belongs to 0, n average minus 1. So that's the difference. This was n traj, this is n average minus 1. Note that the offset n delta t in the three arrays Pn, Fn, and Bn, note the offset. So that's what we have to be careful about. This a certain offset here, which is not here. So this n delta t extra coming around here. Note the offset n delta t in the three arrays. The first initial and average steps of the trajectory are used to initialize these arrays for t equals to 0. Using for a naught tilde of m the instantaneous observable a naught. So for a naught tilde of m, the first initializing value is a naught of q of m delta t, p of m delta t. Then at each time step t equals to n delta t, the scalar product between a and m and b and m allows the computing of the projected correlation function as this. Now, upon evolution from t to t plus delta t, the arrays Pn of m, Fn of m, and Bn of m are appended by instantaneous value of the property. So whatever property we chose, that's going to be appended to the arrays at every time step of its time derivative and of the observable B for the new configuration. So what happens is P, F, and B are continuously appended with the updated values, which we are calculating on the fly. Now, why the oldest configuration is discarded. discarded. These arrays then contain the values of p from time t plus delta t to t plus n average delta t. So the oldest ones are discarded continuously. Average an minus tilde, which would be left untouched when computing a standard correlating function, is updated according to a of n plus 1 is basically a n m plus alpha n f n m delta t for every m belonging to n average minus 1 to 0. So alpha n basically we get as this particular guy. So there are two summations, summation of a n m p n m divided by summation of p n m square. As with the previous method, in the case where p is the momentum of a tagged particle, p is the momentum of a tagged particle, F is the force acting on it, and P square is proportional to the thermal energy. Be careful here, so let's just repeat it. As in the previous method, the first one, in the case where P is the momentum of a tagged particle, F is the force acting on it, and P square is the thermal energy proportionate, and the numerical accuracy increased by computing this average from the instantaneous kinetic energy in the interval 0 to n average, instead of the average temperature over the whole trajectory. Be careful. Now, contrary to the usual procedure to compute time correlation functions, the time span used for performing the average NAV is predetermined. And running longer, the simulation allows to evaluate the correlation function at longer times, but not to increase the statistics. So it can allow us, but that won't help us increase the statistics. Obviously, we need to circumvent this. So that we do by calculating the projected correlation function per blocks of the simulation. So we cannot have a long one, but we can have per block. This algo requires the O of n average of memory size, and the calculation time is O of n average n correlations. N core. So now that we have looked at, studied, and understood both the methods, we will look at the statistical properties of noise. That's what our plan was. So after we do the noise part, we will look at how the results pan out. For now, we will look at how the noise functions, how the statistical properties of the noise play out. So we start with random noise, projected force, and the memory kernel. So let's start by considering a choice of the observable A as the relevant variable P. Its rate of change therefore would be the force F, that is P dot. It will be given by the GLE in equation 5. So equation 5, that's way up there. This guy. AT dot, which in our case is PT dot, which will be called the force, it will be given by that particular equation. Since in that case QF is F and the random force RT is IQ e to the power IQLT QF naught, that is equal to the observable FT plus, and can thus be computed using the algorithm described above in the forward method, it would then, because of all this, it would be possible to test numerically some formal properties of the random force. In particular, since initially R naught is F naught plus, which is also equal to F naught, the memory kernel defined by equation 7 and entering the GLE is equal to the autocorrelation function of the random force. What is that random force, by the way? That is a form of the fluctuation dissipation theorem. The above discussion so far, right now till here, and the introduction of the auxiliary observable FT plus will allow us, so the discussion we've had so far and the fact that we've introduced an auxiliary observable FT plus, it will allow us to compute explicitly the random force and its autocorrelation function as KPT, this expression here. Let's go through this part again. It was a bit complicated, we ran through it, so we'll just repeat this part. So what they're saying is that let's consider a particular choice of observable A, which is the relevant variable P. Okay, that's fine. So the rate of change of P is P dot, which is called the force. How will we get that? We'll get that to the equation 5, which we saw above. Since in that case, where F is P dot, QF is F, and the random force RT is defined as follows. The random force, which is defined as follows, is equal to the observable F and can thus be computed using the algorithm described above in the forward algorithm. What they're saying is that the random force RT and RT is this and the QF is this. So F naught, FT plus can be computed using the algorithm described above. Since we can do all that, it is then possible to test numerically some formal properties of the random force, which is cool. In particular, now with this that we can study some properties. What are those? In particular, since initially R naught is F naught plus, the memory kernel defined by equation 7, which enters the GLE, is equal to the autocorrelation function of the random force. This all as a form of the fluctuation dissipation theorem. So what we studied so far can in short be called as a form of the fluctuation dissipation theorem. The discussion here and the introduction of the auxiliary observable Ft plus allows us to compute exactly the random force and its autocorrelation function as this guy. We can further directly test other properties of this function. How? Now, an important one is its stationarity, which does not follow immediately from the stationarity of the dynamics. Now why does it not follow? Since the evolution of the random force is not generated by the Liouvillean, and since Ft plus is evolved from the initial condition F0 at a finite time t in the past. So, the stationarity of the noise autocorrelation function can be demonstrated as follows. We start from the definition of the projected force F0 plus Ft plus and rewrite e to the power iq q as e to the power minus iq lu q e to the power iql of t plus u q. Noting that this variable here is the adjoint of this variable here. We saw this before as well, so I'm not going to repeat that. We obtain the average of f0 plus ft plus as fu plus f of plus of t plus u, where we have also used the fact that q square is q. Fair enough, that we can do. So this was the random noise, force, and the memory kernel. Now we'll go on to Markovian approximation and the Einstein relation. Einstein did work on Brownian motion, so we use some of his work. Choosing again A as the relevant variable P, we now consider the case where the memory kernel decays very fast compared to the time scale of interest. We are considering the case where the memory kernel decays very fast. The GLE then simplifies to this guy, where we introduce the friction coefficient gamma as we saw this above, so no big deal. We saw this integral above. So in the case where the relevant variable is the momentum of a tagged particle, Einstein's relation states that the friction gamma is related to the diffusion coefficient as gamma equals kBt by md. Expressions analogous to this particular relation can be obtained for the generic observable P. Even though, now we can do this, even though the quantities to which the friction are related are not as simple as the diffusion coefficient. Diffusion works in certain ways. Einstein worked on that. We have a relation from there. Now we can have an analogous one with our observable P, even though the quantities are not exactly related. But then even then we can do it. So we come on to the velocity, force, and noise distributions. Again, we limit ourselves to the case of the momentum of a tagged particle as a relevant variable P. The equilibrium distribution of the velocity arising from both the microscopic dynamics and the GLE should be the Gaussian with the variance P naught square is mkbt, which is basically the Maxwell distribution. In the Markovian limit, the noise also follows a Gaussian distribution with the variance R naught square as m gamma kbt. In general, however, this is not the case. In particular, so we said that in general it's not the case. Out of those not the cases, we take in particular, the finite or long time decay may result in fat tails in the distribution of the force and the noise. Fat tails in the distribution of the force and the noise. Maxwell's are usually very thin. While the velocity should follow the same Maxwell distribution, it follows from the GLE that the difference is Pt dot minus RT between the force and the noise is the sum only of terms involving the velocity, hence following the Gaussian distribution. This suggests that this difference may also be Gaussian distributed in general, as it is obviously in the Markovian limit, since this difference is simply minus gamma pt. So we come from equation 30. Equation 30 was this guy. So we have studied the theory. Now we will go on to the simulation results. So we have a simulation planned out and then we look at the results that we get from there. So simulation results. First, we will visit some numerical details that are part of this. So since the most standard application of the Morris-Van Wyk formalism considers the velocity or momentum of a tagged particle in a fluid as the relevant variable, what it does is, so the most, now Morris boundary can have many applications. The most usual one, the most standard one of this, considers the velocity or momentum of a tagged particle in a fluid as a relevant variable. We have chosen to illustrate two algos on this particular case. More precisely, we consider an LJ fluid, so Leonard-Jones fluid, at a reduced density, rho star as rho gamma cube, or whatever, let's call it any symbol, equals to 0.5, with gamma being the LJ diameter, Leonard-Jones diameter, and reduced temperature T star as Kb by Te, which is 1.5, with L being the Leonard-Jones energy. This similarity system consists of 10 to the power 3 LJ particles in a cubic box of length 10 12.6 rho, with periodic boundary conditions in all directions. Interactions are computed using a cutoff radius RC is 6 gamma. Newton's equations of motion are solved using the leapfrog-Worley algorithm. Leapfrog-Worley algorithm. Take a record of this. Oops, sorry. Leapfrog-Worley algorithm. With the time step of 10 to the power minus 3 T star, where T star is root of m sigma square E, with m being the mass of the LJ particles. So the system is first brought to equilibrium at the target temperature during 10 T star by performing molecular dynamics in the NVT ensemble using the Nose-Hoover thermostat at time constant of 10 to the power minus 3 T star. All properties are then determined from a 10 T star trajectory in the NVE ensemble. We consider first the usual case where both observables A and B are taken as the force acting on the tagged particle. We then illustrate how the present algorithms can be used on the different choice of observables. Be careful of this here. The forward orthogonal dynamics looking back algorithm can be applied a posteriori to a trajectory generated by any simulation package, provided that it allows the computation of the air quantities described by equation 17. That has to be allowed. The results described below were obtained from trajectories generated with DL poly simulation package. We can use them, it's fine. A specific program was written to compute the random force and the memory kernel. In order to accurately integrate equations 11 and 12 to obtain the random force and the corresponding memory kernel, we need both integrations for both of them, in particular at long times. We notice that it is important not to subsample the trajectory. We have to take it at every point. We cannot subsample. And we have to use the momentum and the force at each time step. We cannot take a sample and then extrapolate them. We cannot do that. That will be incorrect. That will give wrong results. So the backward orthogonal dynamics looking ahead only requires data from the previous time steps and can thus be implemented on the fly. To that end, we have written a specific molecular dynamics code. A Worley list was used to compute interactions with a skin at 1.1 RC and updated every 50 steps. We have chosen n average equals to 4000 for the averaging needed for the projection. And the time correlation was actually calculated up to Tmax, that is T star, that is 1000 steps. The projected correlation functions are thus calculated from 5000 time step trajectories. 5000 time step trajectories. For improving the statistics, we have further averaged the projected correlations over 4 successive blocks so that total length of the trajectory n is 2 into 10 to the power 4 steps. That's a long one. Now we will study the autocorrelation functions. Before discussing the properties of the velocity, force, and noise ACF, we first investigate the predictions of both the algorithms for the noise ACF. We have a figure which is here. So figure 1 compares the noise ACF C bar FF of t as the average of F naught Ft plus star obtained by both algorithms to that obtained from the usual correlation functions using Laplace transform. So what we're doing now is we're checking if these algorithms actually work or not. In practice, a numerically stable evaluation can be obtained from the Laplace transforms of the velocity and the force velocity correlation functions. So now we're taking a bit of a black box so that we can actually understand what's going on. What they're saying is a numerically stable evaluation can be obtained from the Laplace transforms of the velocity ACF and the force velocity cross correlation function. What we finally get is the numerical stable evaluation that we get is this guy. The agreement between the three methods is excellent. That's what we wanted. That's good. This validates the two algorithms introduced in the present work for this particular choice of observables. The Laplace route only provides the autocorrelation of the noise. By contrast, the methodologies introduced here give direct access to the quantities Bt plus and At minus, allowing for the study of the properties or the calculation of generic projected correlation functions where A and B are not the force F. So that's what we wanted. We wanted more information. We wanted the actual A and B quantities. Figure 2 compares the force autocorrelation function FACF to the random noise autocorrelation function NACF, which is the memory kernel. As expected, the NACF decorrelates faster than the FACF, which is obvious, even though both coincide at very short times. The longer decorrelation time seen in the negative part of FACF, which is the force autocorrelation function, that happens due to the feedback of the environment on the tagged particle. This systematic feedback is also at the origin of the power law decay of the velocity autocorrelation function. The same feedback is at work in both cases. Now this is at the origin of the decay, but it does not enter in the random noise. Okay. Now since they are based on the Morris-Vanderbilt approach, the algorithms presented here allow to disentangle the systematic and random forces and the effect of the environment. At this point, it is interesting to see that also the NACF exhibits one oscillation. Note that, only one oscillation. A similar behavior has been found in a recent single particle experiment in some other paper. A major difference between the FACF and the NACF is that the former integrates to 0, while the latter integrates to the friction coefficient. That's interesting. This enters the simple Langevin equation in the Markov. So the friction that enters the Langevin equation in the Markov unit, that is the same friction that we get from integrating the NACF. Now we move on to the statistical properties of the random force. Using the forward orthogonal dynamics looking back algorithm, it is possible to reconstruct from each point along the trajectory the projected force F plus for the subsequent times. This allows us to examine numerically several properties of the noise history. Check of stationarity. The noise is the result of the propagation by QL of the normal force from time 0 to time t. So is it here? The noise is the result of the propagation by QL of the normal force from time 0 to time t. From equation 28, we saw above here, equation 28, it's quite above, quite back. So this is equation 28. From equation 28, the memory kernel is computed by correlating the noise after a delay t from each starting point. It correlates the noise after a delay t from each starting point. It can also be computed by correlating the noise after a delay u and a delay t plus u from each starting point as a result of the stationarity demonstrated in equation 29. Figure 3 compares the results of molecular simulations for two waiting times u. This figure clearly demonstrates that the computed noise autocorrelation function satisfies the stationary condition. This figure 3, so this guy, clearly demonstrates that the computed noise autocorrelation function satisfies the stationarity condition. It is a numerical test of this stationarity and also indicates that the algorithm proposed is quite stable. Okay, it's good. Velocity, force, and noise distribution. That's what we'll study as the last part now. Well, not the last per se, but like, yeah, we're almost there. So exploiting further the possibilities offered by reconstruction of the projected force and forward orthogonal dynamics looking back method, we now analyze the distribution of the noise history from a single initial condition. Figure 4, therefore, reports this distribution together with the velocity and force distribution and that of the difference Pt dot minus Rt between noise and force. While the velocity distribution is Gaussian, with the expected variance kBt by m, the force and the noise are markedly non-Gaussian. That's what we said before, we can have wider tails. That's happening here as well. With fat tails, yeah. A similar observation had been made by Sheen et al. For a two-dimensional fluid. some other paper. So interestingly, while both the force and noise display for flat tails, that the difference is Gaussian. Know that with a variance of about 53 Leonard-Jones units. As explained in a certain section 2E3, the difference is the sum of a large number of terms drawn from the Gaussian velocity distribution. In the Markovian limit, it is clear from equation 30 that the variance of this distribution should be gamma square mkbt, that is 41 Leonard-Jones units in the present case. This suggests that this approximation may be reasonable in that case. So it's reasonable. We have a nice value. Now we go to the other observables, short and long range forces. The methodology developed here further allows us to estimate projected correlation functions not only for the force, that is the NACF, but also for any pair of observables. This can be done for any pair of observables. To illustrate this ability on a particular choice of observables, that is in order to gain insight into the origin of time dependence of the NACF. Now we have done this for the two ones, now we're doing it for two other ones, so that we can gain insight into the origin of the time dependence of NACF. More precisely, since momentum transfer inside the fluid arises primarily from the short range repulsion between particles, since that happens, we choose as observables the short range repulsive SR and long range attractive LR paths of the Leonard-Jones potential according to the Weeks-Chandler-Anderson prescription, this particular equation. We have applied two procedures introduced here to the evolution of the forces corresponding to both contributions according to the dynamics and computed the associated auto and cross correlation functions. What we have done here is we have applied the two procedures introduced here in this particular equation to the evolution of the forces corresponding to both contributions according to the dynamics and computed the associated auto and cross correlation functions. The different contributions are shown here in figure 5. It appears that the NACF is completely dominated by the short range collisions. In addition, the dynamics of this projected short range force coincides with the short range force only at short times. As for the total force, the NACF barely becomes negative at intermediate times, while the FACF does. The long range ACF and the cross correlation function do not display such large differences between the dynamics of the normal and projected quantities. You can further analyze relative contributions of the short and long range forces to the friction given by equation 31 in the Markovian limit. So we got from equation 31 this guy, equation 31. What we're saying is we can further analyze the relative contributions of short range and long range forces to the friction in the Markovian limit. What we'll actually do here is that the integrals of the correlations of function of figure 5, so figure 5, that is this guy. So the integrals of the correlation functions of figure 5 are reported in figure 6. These are the integrations of these guys here. For the long range part, the normal and the projected dynamics almost coincide for the long range part, so that the corresponding correlation functions integrate to these guys over here. Similarly, we also find that the integral of 0 to infinity dt also approximates to gamma ls. In addition, we find that gamma ls and gamma ll are opposite. That's new. Finally, the ACF for the short range part is equal to gamma ll for the non-projected forces, but is much larger in the projected case due to the lack of negative part in the ACF. In the projection case, there is no negative part in the ACF, hence gamma ll increases to a much larger value. These observations are consistent with the fact that the integral of the ACF for the total force should vanish. That is 0 to infinity integral dt equals to 0. The average of the integral, average of f naught ft integrated over 0 to infinity with the variable as dt should vanish. The total friction gamma as gamma ll plus gamma ss plus 2 gamma ls is then completely dominated by gamma ss. That is the short range autocorrelation. Fair enough. As a final remark, with that to the end of the paper, we note that the diffusion coefficient obtained from D as 0.33 SJ units is in good agreement with that predicted by the Einstein relation. That is 0.29 LJ units. This is what we postulated. This is what we were right. So that's pretty good. So once again, going to the conclusion, we have developed two methods, one a forward one and one a backward one. What we've done is these algorithms can be used to propagate any observable according to the orthogonal dynamics. We have seen that we can separate long range and short range contributions to the Angevin kernel. We have also showed that the short range is the major contribution to the overall friction, although the other terms are not fully negligible, but it's basically dominated by that. What we've also proposed, now what we've also seen is that the most affected, what we've also seen as the short range force correlation function is also the most affected by going from normal correlation to the projected correlation functions. These algos thus pave the way for analysis of the origin of the friction kernel and the total friction exerted on the relevant degrees of freedom. So further, we have seen the analysis happen, and then we have currently at the moment, as an advance to this paper, for the people who made this paper are investigating the long range behavior of the memory kernel in order to assess the relevance of the usual approximations. Overall, these algos provide a new tool to bridge the gap between the fully atomistic models and effective dynamics described by the generalized Langevin equations. This brings us to the end of our material 2. We are not going to go into the appendix, the mathematics is there for reference. So this wraps up our reading material 2. Thank you.